Yeah, thank you very much. Hi, I'm Tomasz, and today I'm going to talk about two of our projects, CAS and AoT, which you can use, how we can use them to enable symbolic execution on complex system code. This is a joint work with Bartosz, with Pavel, and other members of mobile security team in Samsung or so. So, as we know, there's a whole lot of systems which are written in C and C++, such as OS kernels, basebands, bootloaders, firmware, automotive. And billions of people rely on those systems every day, yet they are inherently unsafe. So thorough testing is really necessary. But working with these systems is also really hard. So usually there's a huge code base. You have various configurations of the same product. And also testing is difficult. So often you have custom hardware, for example, SoC, so the processor on the mobile phone is a custom one. There's no trivial setup on testing and debugging on the device, and also toolchain is not always available. So you can think of, you might not have address sanitizer on a memory constrained IoT device. So as a result, it's hard to run some techniques such as symbolic execution on these types of systems. Just to give you an example, the smartphone, over 70 million lines of code, over 330,000 source files in C and C++, and also lots of developers, many software layers, therefore multiple vectors of attack. And we see that there is, we really need automation tools. So manual handling of these systems is no longer possible. So we propose two new systems, CAS, Code Over Services, and AoT, Auto of Target. CAS makes it possible to provide insight into how software products are made, and also to extract information about the build and about the source code and make it available to external applications. And AoT is built on top of CAS, and it makes it possible to automatically generate testable off-target code. Let's start with CAS, Code Over Services. It consists of two main parts. So it's BAS, Build Awareness Service, and FTDB, Function Type Database. BAS provides information gathered during the build process, and FTDB transforms select features from the source code and also makes them available. In general, you can use CAS for various software engineering tasks like test automation or configuration of our code search. But our focus in our group is on the automation of vulnerability detection. Let's start with the first part, BAS. So there's a lot of information we can mine from the build process, like which tools were used, which files are actually compiled, which comments were invoked. BAS traces the build with very low overhead. So for entire AOSP build, it's 5%. And it extracts information on all interdependencies between software components. So for example, you can ask questions like, if I gave you a header file, show me a list of linked modules where this header file end up. Or show me a list of files which were really compiled into the final binary. And this information is made available to external applications, and it also works at scale. So it's working for Android with over 1 million files. The tracer itself is built as a custom Linux kernel module, and we support all build systems, as well as major compilers such as Clang, GCC, or ARMCC. The information is stored in the database and then made available to external applications, such as web services or configuration or code search. You can generate projects for IDEs, custom makefiles, or compilation databases. The second part of CAS is FTDB, or CodeDB. The idea here is that you use a code processor, which is built on top of libclang to extract certain features from the source code. So for example, types, functions, and globals, dependencies, function calls, initialization and assignment of function pointers, and the source code itself, the selected parts of source code, like type definitions, global initializers, function bodies. And this information, again, is made available to external applications. This parsing I mentioned happens in parallel for each translation unit. So every translation unit is parsed in parallel, and then we have the merging part to make sure that a given type is exactly the same in each of the across the entire source code. Just to give you a better feel for what does it look like, let's see a few examples and also how we can use it in other dynamic testing research. So on the left-hand side, we have the source code of the function, and right-hand side, we have the representation in JSON from FTDB. So we can see things like there's a name of a function. We can see its unique ID. The linkage is internal because function is static. We have the actual body, which is pre and post process also. The location in the source code, literals like
the literals correspond to these two values. We have the functions which are called inside this function, as well as the types used, and also types used in the only in the declaration, and also information on the locals. We also mine information about the member accesses in structures. So here we have this KP arg. We have information on that where we precisely know which structure and which member was accessed, and similar information pointed references like here through kind unary. When we know that there was the reference, we also know that there has been a CAS and a member access. There's also information on array accesses, like here we have the buffer offset and information on the offset, and also on the if conditions. So here we have red less than 0, and we have information that there's a comparison across local variable of ID4 that's going to be red and some integer. And furthermore, so here we have the if condition once more, but similarly we can extract loop conditions as well. Importantly, FTDB also stores information on types, and in particular on structure types. So you can extract information such as the exact size in bits, what are the types of each of the members, the names of the members, and bit offsets of each of the member. So you can use that information to precisely reconstruct this type from the database. And as an example, ref1 here means that the type ID of the first member is 1, so we would jump to ID 1 in the database, and you see it's unsigned int of 32 bits, which is the case here. We also store information on function point initialization. So in this example, we say that the member 0 of the structure is initialized to this function. So this sort of function pointer structure pops is used a lot in the Linux kernel, for example. This is why we have it. As I mentioned, we extract information also on literals, so you can use that to generate dictionaries for fuzzers. Here we have literals extracted with exclamation mark, with star, and this little string. And there are more examples. So for example, you can automatically generate structure-aware fuzzing harnesses for libfuzzer, and also automatically generate syscall definitions. So both of these tasks are normally manual, but you can automate them with FTDB. And finally, we can also use it to generate automatically test harnesses in C with AoT, which brings us to our second project, the auto off target. So the usual way to test software is on target. That is, you test software on the device that it normally runs. For example, if you want to test a message parser in the modem, you set up a mobile network, you send messages over the air. When the modem receives those messages, then the parsing code is invoked, and if there's something wrong, it might crash. So you probably collect the logs, you restart the device or it crashes, and then through multiple application iterations, you repeat the process. So it's not easy, and it's actually the case for more components, the bootloader being another one. So we asked the question whether it's possible to test such low-level system software in C and C++ to provide stronger quality guarantees. And there's a promising technique called off-target testing. It has been used by security researchers in an ad hoc manner. The idea is that let's say you're interested in one function, you take it, you try to pull in all the dependencies, compile the code, and then use the toolchain which you have available on your local machine, like GDB, sanitizers, fuzzers, and so on. So for example, in our message parser, we would copy-paste the message parser code, then try to compile it. It probably misses some types, so we include those types, compile it once more, again, some types missing, and so on. So it's again a manual process and might take a lot of time. So AoT, which is our proposed solution, it makes it possible to automatically generate this off-target code with all the dependencies based on the information extracted from these databases. And those generated off-target instances are fully independent on the original source code and the build. So you don't need to know how the product was built. And also you don't need to have the access to original source code. You just take it from these databases. Since we extract parts of the original system, we also need to initialize the missing program state, which is a difficult problem. By default, we provide support for fuzzing and symbolic execution. And as a result, you can test and analyze and debug pieces of complex software on your local machine or server. And importantly, you can run KLEE and symbolic execution on really complex pieces of system code. Let's go quickly through how AoT works. So first, we need to build the product. It needs to happen once to generate these databases.
Then we extract information on built modules and also on code, types, globals, and functions. Base functions are the functions that we want to test. So let's say our message parser, and we start from them and we recursively pull all the functions that they call. But of course, if we do it like that, we might end up pulling 1/3 of the original target. This is very usual for Linux kernel, like these dependencies are going really deep. So you need to cut off a certain point, and it usually happens for us at the module boundary. So all the functions which are in the same compiled module are treated as internal. We keep them. For the other ones, we generate stubs. Now, once we have the list of functions we want to include or stop, we also pull the required types and globals to resolve dependencies and generate initialization codes such as initialize pointers. And finally, you can run testing, analysis, symbolic execution of the generated code. The problem of program state or missing program state is a very difficult one. So let's take this example. We have this simple function foo. It takes a pointer. Of course, if we don't initialize memory for y, we immediately crash at line 12. But it's not always easy to know what to initialize, because you might have a void pointer and only learn inside the code what's the actual target type of this argument. You can also take a member and use offset of operator. So for this very simple code, to properly initialize the state, you need two objects, like one of struct A, the second one of struct C, and furthermore, you need to set the pointer member1 in struct A to point to member2 in struct C. In order to discover which types to initialize, AoT implements a heuristic based on static analysis of the information provided by FTDB. It works like this, that AoT reads the code line by line, and only looks at certain code events such as casts, member accesses, use of offset of, because these can affect the type of the parameter. And then we only initialize those structure members which are actually used. This might be important only, I guess, in some targets. In Linux kernel, it is very important because some of these structures have they have a lot of members. Once we initialize the memory, we also need the right values. So in this example, if x is anything other than size, we never execute line 8. Or if selector, which is based on return value of a function and a global, if it's greater or equal size, then we will never execute this return statement. And in order to discover program state, AoT implements hybrid fuzzing approach. So we first run KLEE and then AFL. The idea here is that you mark entire program state as symbolic. And thanks to symbolic execution, we can actually run the code without knowing the original program state. So we'll let the executor explore as many paths as possible, which of course leads to false positives. That is, there are certain paths or certain values which are allowed in off target, but will not be allowed on the device because we are missing constraints from the device, which results in false positives. And we have a mechanism to filter them out based on data flow sanitizer. The way it works is that we apply taints to user controlled data. So let's say if y is user controlled, and if selector through symbolic execution or fuzzing is -100, but it's not user control data, we might ask, well, yes, we crash here, but did we even touch user data? If not, we assume that it's a false positive, so it's not coming from the user. There's another source of false positives, that is the initialization itself is heuristic. So we might guess the wrong type to initialize, basically. So in the end, the manual intervention will be required to find real bugs, as we will see. So we evaluated this prototype on 4 targets: kernel from the Pixel 6 phone, the Linux little kernel embedded operating system, UML bootloader, and a module from Osmocom. In total, we were able, I'm not sure if it's very visible, but we were able to create over 52,000 instances of these off-target programs. And majority of them, from 85 to 94%, we were able to compile them straight away without any manual intervention. On average, on the largest target, which is the Pixel, it took 1.5 minutes to create the off target. And also it builds quite fast. So it's 21 seconds on average. But also take a look at the number of types it takes on average to resolve dependencies. It's like 1.7K for AOSP. So it's going to be hard to do it manually. Like you might need to go through multiple iterations. In order to see how good those off-target instances are, we run an automated test, not to find bugs, but just to see how many of them we can immediately execute with KLEE and AFL. And again, from those which compiled from 93 up to 99%, we can immediately run those tools. We achieved line coverage from 46 to 92% and generated a few test cases on average. As I mentioned before, in order to find real bugs, however, you need manual intervention because there are still false positives which cannot be filtered with the heuristic. And for that, we did another exercise that was the bug finding campaign on a Linux kernel entry points from 2 pixel phones. So in total, we took over 9,000 functions. We generated off targets for them and run KLEE and AFL++. Now, then there was the data flow sanitizer filtering, which left over 312 of the soft targets to review. And after manual review, we found 7 bugs. So 3 of them were our new security issues, which will be assigned CVEs. 1 was an old CVE, which is already fixed in the newer release, and 3 of them were non-security issues, which we believe is a good result because it's a high-profile target and also very well tested. So limitations. AoT currently only works with C code, and we also don't translate assembly across architecture. So you can include assembly, but if the original target is in a different architecture, you will need to somehow translate it or deal with that. The incomplete modeling of program state or this heuristic for initialization can cause FPs. And actually, I believe that program state initialization is the open research problem. So I think it's an orthogonal problem. Support for C++ is in progress in CAS and AoT, and we would like to improve state initialization. The idea is to perform memory dumps on the device and then use that dumped memory to plug it into the off-target code to get the real values from the device. We have a new tool, KFLAT, for that. So just to sum up, I just presented 2 our projects, CAS and AoT. So with CAS, you can extract information on the build and on the source code, make it available to external applications. And as we've seen through examples, it can also be used for other dynamic testing research projects which operate on such information. And AoT, which is based on CAS, can automatically generate usable test harnesses in C. Importantly, it can be used to run KLEE on very complex systems code like Android kernel. And indeed, we can find bugs with them, of course, with manual intervention. The core engines of the tools are available as open source. So is our new tool for manual dumps, KFLAT. Bartosz gave a talk on CAS, so more details in that talk on Linux Security Summit. It's already on YouTube. And we have published this as an ASC paper, which is upcoming. So I'm going to present it like in a month. And the preprint is already online. So in general, we welcome feedback, contributions, and bug reports if you find these tools useful. And I guess with that, I would like to thank you for your attention.